Okay. So, welcome everybody to this wonderful class. You had, I guess, a genius class yesterday as well. So, as you might remember, I came in yesterday and to ask you if you want to do something more hands-on or something more lecture-based. And there were 3 people who raised their hands that they want to do something hands-on. Hence, we'll do something hands-on today. So the class today is structured in 2 parts. You see that as well in the announcements. So we'll have the little lecture making things part 1. Depending on how long this takes, we can as well skip part 2 and go directly to the demonstration. Today's demonstration, you have a fire, that's in the second announcement. Where you have a ring, you have that in Rhino. Some of you have it open already. And what we will try to do is we'll see how we model something in Rhino with the advantages of Rhino, which is basically curve-based and extrusions and all that. Curve-based and lofts and flow along curves, and things that you have seen before, sweep runway, 2-rail. And then mesh it to become a mesh that we can use in the common software such as Modo, Blender, 3D Max, Maya. I will demonstrate a bit of 3D Max because we have it here, but you're very free to use the software that you are most familiar with. I don't use Max myself that much anymore. I used to use it exclusively. I switched a lot to a software called Modo, which you can, I think, even have a free trial student version of. It's from a company called Foundry. It's very, very fast for 3D modeling in terms of poly modeling. And it is as well more advanced in that than 3D Max is. But we don't have a license for it in school because the school decided to save money and scrap the license of Modo last year. So that was that. And then we have in-class working on the design of a ring. So using, well, Rhino Modo / 3D Max and Mesh Mixer. And all rings that are finished by the end of the class will be 3D printed for you. Means if you can send me an email by the end of the class with the STL file, the 3D printable file, and the file can be printed, then I will print it for you, and you can have a ring, which is fun. You give it to somebody that you like, wear it yourself. It's just a small incentive, but there's no grade for that assignment. So you might as well just do nothing at the end of the class. Then you don't get a ring, that's cool, nothing wrong with that. So it's just like, if you want to participate, you participate. If you don't. Sure, that's the easy one. Okay, so with that, we start the attendance. Chuck Wing, here. Han Yin, yep. Ching Ho, yep. Kai Hong, yep. Tam Yu, thank you. Ping Ping, yep. Yuki, yep. Chuck Yin, yep. Park Lun, yep. Hui Ying, fantastic. Chun Ki, Kwai Chi. Hugh Lam Nao, thanks. Chuck Kim. Hugh Wa, lovely. Taki. Xin Yao, thank you. Yi, thank you. CY, thank you. The Q. The Q. The Q. Nan. Nan. Yi Lam. Thank you. Chen. Ho Nam. And last but not least, Charlotte, aka Money. Thank you. All right, everybody present apart from Sir Q. Very sad, hopefully. All right. Okay. Just a quick reminder, please, that your replication and transformation assignment is coming up as well, not directly, but keep it on your radar. You see, 25th of March. So that seems to be quite long from now. It's not that long. And remember, you will have to make a 3D scan replica of the object that you have been given. And by 3D scan replica, I highly recommend, unless you are the kings and queens of 3D scanning, that you're using the 3D scanner in my lab, because it's a lot faster. And that you prepare yourself with baby powder, hairspray to dull surfaces that are not 3D scannable. The replica means coming as close to the original geometry as possible. So doing a little bit of wibbly wobbly photogrammetry scanning with your phone does not cut it well in this exercise. Okay? So you can write me an email. I'm here most time of the week. I have assistants as well that are there. They're not there to do it for you or help you, but they give you access so that you can use the 3D scanning equipment. Okay? Okay. Good. I think then we can start with today's little lecture about making things. So this is a bit of an inspirational lecture where you can see a length and breadth of projects and technologies involved in that hopefully stir up some interests or ideas of what you could do with your assignment number 2. So making things, I relate this to the notion of digital craft, which is to understand the existing methods of doing things like carving, weaving, blowing, ceramics, glass, wood, stone, things that we have been exposed to for a long time in our life, and seeing how one could augment or extend these with digital tools that are today around. So this is what is a glass blowing hut. There are not many of those in Hong Kong. There is some glass blowing in Hong Kong, in Kai Tak, on Lama, in Prince Edward in the Sheckett May in the JCCAC, and obviously at Baptist U they have a glass blowing shop. I went there in 2018, never done any glass blowing, and it was quite interesting. I was invited artists there to work with glass blowers and extend their craft with what I do in digital design and particularly in additive manufacturing, 3D printing. But if we can think a little bit about the notion of craft, it's something that seems to be old-fashioned to discuss, although it is a very emergent problem that's very acute. Particularly in Hong Kong, you have seen it in the last 50 years, how many crafts have disappeared. Much knowledge about how to handle material, how to have ceramics, for instance, have disappeared. Ceramic painters have disappeared almost entirely. There is a wonderful museum or a wonderful organization called Crafts on Peel, which is on Peel Street in Hong Kong, with a wonderful lady called Penny running it, a Hong Kong lady whose mother actually was a seamstress, so somebody who makes seams and knitting and textiles. And her space, Crafts on Peel Street, is really dedicated to seeing if some of the crafts of Hong Kong can actually be preserved, but not in a stupid way like old-fashioned, like, oh, there's an old man, there's a Sifu who can do that and that, let's exhibit what the Sifu does, and then the Sifu dies, and then the knowledge is gone. So it's kind of the same stupid thing. But to pair up crafts, local craftsmen, crafts practitioners, this is not a male-female game, with artists. So if you are interested in seeing how far you can push digital design, for instance, or the way how you make things, it's an interesting starting point to talk and to see how they can help you. Well, I said that I had in the background this text, which talks mostly about how the idea in writing terminology, so for instance, Richard Sennett is a sociologist, a Canadian sociologist, is being discussed recently in the last decade as something that is less so the notion of only a person like with a knife doing carving or pottery or so, but it's more of an idea of how to make things in itself. And that's quite interesting because in his book he discusses also the craft of computer science, which is a bit strange. But it's an interesting notion to think about that how craft had been taught and is taught, usually by lineage, so one master and apprentice and teaching it downwards, and then if the lineage is broken or so, then the whole knowledge is lost. It's actually something that could be maybe articulated further. It's the impulse to do a job well for its own sake, independent from medium or material. The notion of giving a shit, basically, of not just working it off or generating, but being involved in the process of the work. And I thought this was quite interesting because if you are going further, if you really want to immerse yourself into some philosophical writings, we have some great philosophers here in the school, like for instance Yokoi, who is a intellectually descendant of Heidegger, a German philosopher who brought up the notion of what then technology is and the making of an artwork, how this is on the one hand side the technical specificity of understanding how something is done towards the point of what is done, or bringing forth the true into the beautiful. And that makes making things a very interesting thing. Obviously, Heidegger is a deeply Western philosophy of technology, but Yokoi, for instance, who is from Hong Kong and a trained computer scientist, in case you have never had it in class, and undergrad, I don't know if he teaches undergraduate or postgraduate, is a trained computer scientist who then went to Europe and studied philosophy, who then comes back to Asia and, for instance, published his very important work on cosmotechnics, which is combining an Eastern understanding of technology and its application, which is a Western understanding of it. So that's a quite interesting start for you if you want to go more into the direction of understanding what technology actually means. And that does not mean technology means I have a mobile phone and I can Google. It means an understanding of how to use technology and not be used by our technological environment. Now, two of the digital processes that I like to discuss quite a lot in my writings, and again, this is not necessarily this hands-on class, but there has to be some theoretical background to what you do, because otherwise you just do things mindlessly without any form of thinking about why am I doing this here in this class. Of course, yeah, you had to take a class and it's 6 credit, but somehow one should as well maybe have a notion of I actually can identify with the work that I'm doing. So one of the things that I work a lot with is the notion of reification and sublimation. Reification is the act of making something into matter, while sublimation in physics is a way of making something from a solid form into a gaseous form. And that can be translated towards, yes, for instance, 3D scanning. We are making a digital copy of something that has physical properties. And then reification, the act of making something physical that previously was not physically there. So yes, we could 3D print something, for instance. And those kind of pairing between amalgamation and augmentation, sublimation and reification together in the context of Heidegger's philosophy of technology is an interesting starting point, or actually a starting point to describe our relationship to computer-aided design, the working of taking something physical into digital and something digital back into physical. Now this is a lot of difficult work, and I hope you did not fall asleep yet. Hopefully you can make some nice images of it. So I'll show you now a lot of works that have basically all to do with exactly that pairing of sublimation and reification, of scanning and printing, of material narratives, and as well of copies, because replica, assignment, blah, blah, blah. So how to deal with that. So in this work here, for instance, this is a work I produced in 2005, so that's, 18 years ago. Jesus Christ, how did that happen that we actually talk about something that's 18 years old? And these two little fellows were 3D scanned bones. This one is a shoulder bone of a lamb, and this one is, inside it is a bone of a tortoise, the entire bone structure of it. And these things have been augmented, or have been fitted, with something else. In this case, this is a larger project where I speculated upon the idea of creating tiny relics that are perfectly fitting together between something that's 3D printed, so these elements are 3D printed, and the natural found object inside. Now this was a lot before you could do photogrammetry with your mobile phone, so it was quite difficult to make these, but the context, the cultural context mattered a lot in these. I found these bones on a journey, on a travel. I was actually still a student. That was one part of my graduation project. On a field trip to Cuba, Havana, and they were on a graveyard there. So I took these bones from a culture that is known for sacrifices on graveyards. So yeah, it's a little bit scary, a little bit weird. And I wanted to understand how these, in a cultural context, mini deities could work. Could basically inhabit the bones on the graveyard of Havana. So I basically 3D modeled them after researching a lot about the local culture of Santeria, which is a mixture between African slave religion and Catholic religion that was brought over to Cuba because it was a colony. So it's a weird so-called syncretic religion that kind of like works with images and shapes and forms from two cultures, two very different cultures, the Christian culture from Europe and the African Yoruban religion from Africa, from West Africa. And the result were these kind of little experiments where a found element that's unique, a bone, absolutely unique, every bone grows differently, perfectly fits a 3D print and thus creates these kind of tiny miniatures. You see that together, the bone is completely inside and outside the 3D print. So for this, for instance, just on a technical level, I had to take the bone apart. So I scanned the bone, then I had the 3D scan model, then I took the bone apart, because bones actually, when they're dry, they're like ribs So you see these are here, the lines. And so, you know, maybe it's a quite interesting thing that a tortoise is like a rib cage of us, just mutated. So basically the ribs grow into each other. So this is a rib, and 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 that basically makes a shell of a tortoise. So I could take it apart and then stick it back together after 3D printing. So I was not 3D printing into the skeleton as some might mistake. I had to assemble it back after the fact, printing, assembling, and putting that together. There's still no glue in there today. It's actually the little tiny fractures between the bones holding together. In the end, what I created was a very large, just about a meter tall 3D print. This is again 2005, so a bit different. Imitating the language of the scan into an architecture. Remember, I did study architecture at the time. It's a bit different. So yeah, 2006. Drafting 3D scan narrations into material and cultural context. Culture, because of the way where I took it and how I worked with it. Material narratives, interestingly, because on that graveyard in Havana, all the gravestones are made from marble, but marble does not exist in Havana. It was brought over from Italy. That was before there was an embargo against Havana, basically in the 1920s last. So you would have this strange material narrative in a place that doesn't even have this materiality anymore. And that was as well when I started to 3D print for the first time, because these 3D prints are made from calcite, basically plaster, chemically the same as marble. Now this here, this guy on the other hand, is something else. This is 3D printed from a resin, a UV resin, and the geometry that you see stems actually from my own body. So after working with found objects and fitting them perfectly into each other, I started to work with geometries that don't exist, or at least they are not accessible, because this is part of my heart. So I had to get an image of my heart, a data, a 3D scan of my heart. But I didn't go to hospital and had them cut me open and scan my heart. That's a bit difficult. I don't have scars here. Instead, I used magnetic resonance imaging. So that's what you do when you get a CT scan or an MRI scan. You actually get data to the degree that you can, through actually in a funny way, the same process that you used in photogrammetry, you can, or a similar process, you can reconstruct from the X-rays, from the area of X-rays, a 3D geometry. Now my heart doesn't look like this. If it would look like this, I would have a serious problem, because that's not how a human heart looks. So I took only the beginning of the heart and the organs, or part of the organs, and recreated this new type of body. So this was only one of a large array of 3D prints. That would be partly stemming from the original data and partly extending it forward into something else. This is actually some of the residues of it in my studio in London. Now on a black marble plate, almost like a gravestone. So again, material narratives are very, very important for this. Now the work doesn't exist anymore, which is okay. So it's sightless, it's not found in the sense of the bone. It doesn't have a real physical object to relate to or to attach to. It's not a copy, it's an extension. Now this one gets even more interesting, because here again you see a human body. So this would be a kidney. That's the liver, and these are the main aortas running through here. So I 3D printed a part of a human body. Now what type of part did I use? This is not me. This is a guy's body called Joseph Paul Jernigan. He murdered a security guard in the US while stealing a microwave. He was not a very smart man, that's for sure. But he donated his body to science after his execution in Texas in 1996. So he got executed by the state of Texas by a lethal injection. Not a good practice, but we don't need to ethically debate this in this class. And what he did then, he donated his body without knowing what will happen to his body. Now comes the controversy, because what scientists did to his body is they have frozen, and then they cut it into 1 millimeter slices. So So they basically made a photo of every millimeter of his body, cut in this direction, cut, 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 cut. And the data of his body today is called the Visible Human Project. And it's a public data set, and you can have access to it actually. So there's 1,894 images of his body, because he was 1 meter 89.4 meters tall. And the interesting part of this is that as this data set is public, you can use the photo to reconstruct his body, which I did using an MRI software. And then I printed 4 body parts of his body: his lungs, his heart, his abdomen, and his pelvis. And I submerged these 3D printed elements. This is a SLS work. So SLS means selective laser sintering. It's a nylon like that. We will have a class on 3D printing. And in the porosity of this material, I nested microcrystals that then grew into these very large, these are all big crystals, like about that size, that very slowly, during the time of the exhibition, grew into the body of this convicted murderer. Now, why did I give this body such special attention in this beautiful crystallization? I did not. The machine I invented at the time was to roll the crystal onto the material, depending on the interaction with its environment, depending on the interest of visitors. So if no visitor online or in the gallery would have come or showed interest, being present, very simple sensor system, I mean, you've done more difficult stuff already in this class, then the heating elements in this machine would basically stay cool. And that would cool down a supersaturated fluid, and that would mean that those crystals would be microcrystals like the sugar in your tea. Crystallization works usually by supersaturated fluids cooling down. So the example is, you go, you get yourself a tea, you make it very hot, you shove 3-4 spoons sugar into it, it's very sweet. If you throw that against the wall will cool down the tea so fast that the wall will be sticky, but you won't have a sugar crystal on the wall. But if you would, for instance, put a little thread into this tea, and you keep it nice and warm, and slow down the temperature very slow, cool it down very slow, then you would get on that thread 1 big sugar crystal when the tea is cold. That's the same here. It's just not sugar as a crystal, but aluminum potassium sulfate. So I did not do this. The audience, the time and the body of this murderer basically was grown through an interest. So what I'm saying with that is, if we talk about making things, is each of the material that we're using, even 3D print material, a material that everybody thinks is completely useless in the sense of, yeah, you can 3D print it, and then what? Here it is, ta-da! It doesn't have the same narrative as gold or wood or porcelain or shells from the beach or sand. All these have like our emotional values, but 3D printed material, each material can have, if you look into it, the ability to be combined, connected, to have its own basically life. And this material, SLS material, is really, really strange, because through the process of 3D printing, this 3D printing, not other methods, it creates a porosity in the surface that is perfectly for bonding crystals into it. So even 3D prints have their own material narratives and their own properties. They're not just representation of something else which you couldn't do because you didn't have the money to cast it in gold or whatever. Right. Now another project is a project that deals with the Cantonese opera. So these colors and shapes might look familiar to you. It's a Chinese Cantonese opera, very famous one. It's a very kitschy one as well. It's the Flower Princess. And it has 2 main characters. And it's a very funny little opera because it basically mimics back the idea of Romeo and Juliet, like the tragedy of misinformation. The tragedy that Romeo thinks that Julia is dead, but she didn't take the poison. You know that story, right? Does anybody know? Yeah? Okay, good. So it's all about like miscommunication. Like one assumes the other and the other assumes the one, and hence you create tragedy out of the unexpected. These two masks were projection mapped, they're 3D printed, and they were communicating with each other during an installation, continuously misunderstanding each other, to the point that the projection mapping would then indicate that one of them dies. Maybe there's a video, let's see. No, I'll show it to you later again. We'll talk more about 3D printing anyway. And this is a project about jewelry. Today we do a bit of jewelry, because jewelry is fun. I mean, it can't really hurt, right? Now, what do we do with 3D printing in jewelry? Yes, we can 3D print in gold, we can 3D print in Kappas metal, we can 3D print in wax and then cast it, so that's all the traditional ways to do jewelry. But what about actually using methods of making to the advantage to do things that you couldn't do in any other way? So this is a collaboration with a silversmith, Sylvia Weidenbach in Germany, although there is no silver in there. And what we created is this object here, and it's entirely 3D printed. Even the chain is 3D printed. Everything is 3D. But you can only get it like this. So you can purchase this. And it's very pretty. It's about this big. And then you have the problem what to do with it. Because you can clearly see there's lots of holes, that there is a chain inside it, but you can't get the chain out. So you have to break it. You have to break it in two. You have to destroy the object if you want to wear it. As they're both identical, you can't wear two because that's a bit stupid. I mean, unless you have two dangling around that look the same, doesn't really make sense. So you have to give one away to a friend. So the idea behind this was to do something that's so specific to the technology of 3D printing that you can do the most crazy geometries that you cannot in any other way do, that we basically printed the chain to be inside here, and then you had to destroy it. And that is funny because in this way you can build in a narrative into the production process. So a narrative of friendship, of love, of sharing can be actually part of how you make something. That doesn't have to be gold, again. It can be simply the fact that through the method of making, you're implicating that something has to happen for this to function. And you can never assemble it back. Once you break these tiny pins that we built in here, you couldn't glue it back. So you couldn't even glue it back because they were very fine, very small. When we worked further on this, it became a bit funnier because then we thought, okay, now let's make some precious stones in it. And well, I don't like precious stones very much, like gems or so. They're very expensive and usually they're quite. Many of them are done in a nasty way to the environment. Some of them are politically very sensitive. But I like these Swarovski crystals because they're just stupid. I mean, you go to the shopping mall and there's a Swarovski, and you know, Swarovski crystal is literally glass. So they sell you glass and then make it very expensive. So I thought, wouldn't it be nice if we could make something where the labor process is so reduced that any baby can assemble it, like literally no skills whatsoever. You just get a bunch of little glass stones and you go pop, 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 pop. So what I designed here is a little 3D element that has a tiny little lid, like a tiny little overstep like this. And Swarovski crystals are actually done by machines, and not even polished by human beings. So they're extremely precise. And that means you can literally get a handful of these glass crystals and just literally pop them in. And that was quite fun because you cannot, this is called a pavé setting. And when you buy, for instance, a ring with a pavé setting, yeah, they get ultra expensive because doing this by hand to kind of make tiny little things where crystals or diamonds can be held as one surface. So pavé means you cover the entire surface with crystals or diamonds or so. Yeah, it's labor intensive and it's very expensive. While if it's 3D printed, here's one of the results. You can literally pop these crystals just in, like literally. It was really fun to do this and very shocking to some of the jewelry because we were so rude. We combined crystals with plastic. I mean, who does that, right? It was good fun to do that at the time. Now I want to go a little bit back as well into history of this course. This course is SM3804. But before it was SM3814, it was a crazy collaboration between Professor Scott Hassels, who you might know, who's leaving us at the end of this year actually, for retirement, and myself. His course was called Future Cinema, and my course was called, yeah, that's a good one, something. I remember the course code, 3713, but I don't even know what the name was. Anyway, one day we sit together and we go like, why don't we do something insane? And we're like, oh, okay. So why don't we make a course where students get a budget and make a project, and we're gonna create in the media theater downstairs, we're gonna let them go wild with any chemicals they want. And yes, we did this. And yes, nobody got injured, and yes, that is very lucky because some people really try crazy shit, like hydrochloric acid and other things, where you go like, should maybe not be in this building, should maybe not be in this class, hopefully you're careful, because otherwise your eye is gone. But the nice thing about this was that due to this, and there you see some, in these small photos, you actually see, oh, let me zoom in, because they're really crazy. See, these were our working environment. So you see people were basically half exploding things, mixing crystals together, trying laser cuts with some sort of glues or reactive paint. It was very fun. This is actually paramagnetic fluid, I can guarantee you that. She's not wearing gloves, so that's already not a smart thing. This is maybe one of the dumbest images I can think of. It's like you're very, very focused here, at least you wear some safety glasses, with a pipette with ferrofluids while you're holding a box of a vial of other ferrofluid. That's maybe not the right way to deal with this. But it was fun. It was good to do it. And the results were fun because we could create something like the autopoiesis between digital fabrication and material behavior. And one of the really great artwork I thought was this by Sam Chan, which is a perpetual chemically growing flower that grows and dies and grows and dies and grows and dies. It's a urea crystal, and this is the dehumidification agent that you would find in any supermarket, maybe in your own clothing shelf today. There's a little opening and closing mechanism, and there is just an opening mechanism to let in air from outside. So when it would be too humid, the crystal would die. Warm, when it would go drier, it would soak up the fluid here into the paper and grow back. So that was actually a really nice little machine. I'll show you that video. And then there were some other stuff. Smart music. Oh, no, there's no people there. No. We had a lot of fun with these things. This was actually really good fun. Like putting actually glow-in-the-dark powder into wood. That was quite interesting. Very smart idea of how to change the perception of wood. Glow-in-the-dark in flowers. Those were easy ones. But I did like this wood thing. It's a very simple idea. That just rubbing the powder into the surface, and all of a sudden you kind of get this complete other material behavior. And a lot was, in that case, as well about how do you film it, how do you document it. So that's, because obviously there was future cinema in there. That's a bit less today. Yeah, it was a great class, very fun, lots of interesting techniques. And I thought it would be good to show you like where it's coming from. But where they still exist, and that's quite interesting, and I'm working at the moment as we speak on to bring back this website. So this website actually still exists. If you Google skunkworks.scm.ctu.edu.hk, it's not listed on Google, so I will repeat one more time. skunkworks.scm.ctu.edu.hk. I would write this down if I were you. skangworks.scm.cpu.edu.hk. And what you will find if you would look there is you will find all the recipes and all the manuals of all the projects that were done in Skunkworks. And I'm working now on actually adding all the projects from 3804 into that as well, with all the recipes and all the makings of it. Oh, she found it already. So it's really fun. You should try it out because you can maybe get crazy good inspirations for your project, and it's got a lot of good tips on how to run the project. And your projects will be part of the new version of this as well. The interesting bit with this website is that you could look actually by reaction. So you could say, I want to do something with water exploding, and then you would already get those projects that actually include water and explosions. Anyway, we talked as well about the other projects, so making things. I do like to hope to instill on you that you can do big things. You don't need to do small things just because you like media artists or so. Like CNC gives you the possibility for very little money to do very big things. So the budget for this pavilion were three sheets of plywood, and I think including transportation, milling and material from Shenzhen, it was less than 700 Hong Kong dollars. So that's a pretty precise, big structure for 700 Hong Kong dollars. Maybe even less than 600. So some projects that we made then, there was more like the notion in there that let's not, so these projects don't use any glue, any screw, nothing. They just use wooden elements and connecting elements, so smart little connect. So we basically just take it, mill it, here it is. So we have toys, for kids, nice assembling process, furniture. This was actually a really good chair. Really complicated. This was just one sheet of plywood. Very nice. And production for one sheet of plywood, including shipping to Hong Kong, was 250 Hong Kong dollars. So getting a plywood completely customized chair as a product of 250 Hong Kong dollars. And that's high grade plywood. That's not the shipping plywood. That's the high grade. So Russian birch plywood, high density marine grade, meaning very, very beautiful material. And the other course I thought that would be quite interesting to remember is a course that I ran for postgraduate level, but it's a quite interesting project where we looked a lot into different history time, historic era. This is done with the Rococo, and tried to combine historic ways of making things within new materials. So Rococo has this element of very, very elaborate ornament. But combining it with 3D printing and 3D scanning elements, you get this very strange, almost like steampunk effect, where the elements devoid now of the materiality of being the tradition. Because this glove should have been made out of silk or maybe metal at the time, and the design is entirely in a timeline that is not today. But bringing it into a polymer 3D printed design changes its narrative drastically. So it almost becomes like something you would see in a Japanese anime film, maybe, being materialized, rather than being in a museum, where original Rococo elements would be. So yeah, a lot of, this was actually one of my favorite, and this is in 2017, so we're talking before the pandemic. It's a student who made a mask, a breathing mask against, a respirator against smog. Hilary Shee did this. Against smog, which at the same time had all the ornamentation of like the Rococo time, like the rocaille and the asymmetry, and even the mask is pseudo-symmetrical, so elements are symmetrical and pseudo-symmetrical. So it was very interesting to look into a different time period, so you could look into the Song dynasty or so, and change the materiality and bring it into a different time zone. And with that type of design language, then design something for today. Of course, a mask is very useful today. Hopefully for not too much longer. There are many cool projects. One of the things I wanted to make you aware of, and this course and the Skunkworks ended up then to be the creator for the Create SCM, the Create project in the library. So if you go to the CTU library, they have a place called Create. Has anybody of you been there? Nobody has been there, right? Okay. It's a very interesting place because I basically set it up for them. And it's a place for exploration of creative technology. That means they have quite a lot of stuff there. So they have a 3D scanner, they have a Flashforge 3D printer, they have a laser cutter, a photo studio, Arduinos, Makey-Makeys, and even like a green screen. So it's an interesting thing that in the library, right at the beginning, when you go into the main entrance of CityU, the AC1, to the right is the extension of the library. You have a full fab lab. You can actually go there and print there, and they're very, very cheap. So laser cut stuff. So that's the space. You've got the various stations. This is the laser cutter, the 3D scanner, the 3D printer, the photo studio, and actually work there. I know many people never went there, but it's not, I mean, okay, it's not as the ultra high-tech stuff you get in Shenzhen, because that's companies and they're more expensive. But it's a pretty good place to basically start and learn about all of these tools. Like from the printer to the scanner, which you anyway have as well, my lab, to the laser cutter. It's a really cool Japanese laser cutter. Green screen studio, mini studio. You have actually, this one is a really cool one. We bought this one for them. It's like for product photography. It's basically a light box where you put your whatever object you have in, and then you have perfect lighting conditions. So it's an easy way to actually document your work here. Just go there, use it for half an hour, get perfect photos of it. Yeah. Now this last work in this project deals with exactly your project you're assigning to. So what you see here is the copy of a copy. So there is an original, there's an original intervention, there's a copy of the original and the copy of the intervention, and the reconstitution of the copy into the original. Sounds a bit stupid, I get it. So I will go through it a little bit more, and that brings us back to the glass where we started. That's my studio in London. That's my studio that was my studio in the artist residency. And when you look, so 3D scanner, very important, 3D printer, huge hand drawings, yes, I can draw by hand, guess what? Lots of experiments, lots of glass experiments, lots of normal tools, gas, notebooks. So this literally is like where I was working. It's nice in the middle of nowhere. Can only recommend it. So what is this? This is the pelvis bone of a deer, the hip of a deer. Okay, why did I use the hip of a deer? Am I such a freak that I need to use bones all the time? No, I found it there. It was lying around. So I'm like, okay, that's a unique found object. Yeah, we're in the middle of the woods there. That's not in the city. That's 30 minutes drive away from Seattle. So it is literally, I mean, people live there, so you open your cabin door and there's a deer just walking by. It's like they're used to artists for 30 years, so they're not even shy anymore. Yes, there's brown bears as well. They don't look at you like that, but even they don't seem to be more accustomed to artists doing stuff in the woods. Anyway, found a deer skeleton, saw like nice object, like it. This is where these are the sockets for the legs of the deer, so that you can maybe imagine now how it's upside down, yeah, maybe kind of fish. Anyway, and then I thought, okay, let's do the same one I did in 2005. Purple skeleton, deer skeleton. Because I didn't know what to do with glass, because I'm not a glass maker. So why the hell would I know what to do? And I just thought I do 3D print, so let's stick to what I know, make a copy of something. And to make a copy in glass of this, in the traditional way, takes about 3 weeks, which is quite painful. And that's not you 3 weeks working, that's like making a mold, getting the bone out, filling the mold with a wax mold, putting a cast around the wax mold, burning out the wax mold, filling out the cast with glass, filling up the kiln, blah, blah. It's very, very difficult processes of making a copy of something when making molds and casting them. So this took 3 weeks. In the meantime, I did some other projects. But what was interesting about this is, if you make a copy of something in the physical world with the physical tools, it is very hard. Very, very hard. While if you make a copy in the digital world, it's very easy. That was the project that you saw with the turtle, using some of the scan, this is the 3D Max. Very, very easy, this kind of sublimation. Now if we go back to the deer, what I did is I extended the deer, similar to what I did to the turtle. I made something that lives on the little bone. Here you saw that, and here, that's what I did to that. Now this is interesting. This is very interesting, because this is where I failed a lot and learned a lot, and think that where I can pass on knowledge to you. So, I found the bone. I made a copy in glass, so I changed the narrative of this entirely. This one you would not put onto your nightstand, right? Who wants to have a bone of a dead deer on their nightstand? Nobody. That's creepy, that's disgusting. But who wants to have a nice, shiny, polished glass that looks like a bone? Already half the class I can see your eyes are not true. Like, what's wrong? Then I 3D scanned this guy, because I wanted to test if this guy, through its traditional method, is as precise as this guy. Okay, so I 3D scanned it, and then I 3D printed something in a polylactic acid, which is this. That's just a PLA. And it fitted. So that was the interesting bit. That means that the traditional copy of the original is precise enough for a digital fitting, for a convergence between something that is entirely digitally made and something that's entirely analog made. But then I went a bit crazy, because then I thought, let's do the reverse. So what happens if I use the techniques to make a copy from this guy to this guy, reversely to make a copy of this 3D print into the material of the glass? It did work, but it looks shit. It's very rough. Plus it took like 3 weeks. Plus it broke. A lot of things just don't, I mean, yes, it kind of is, ooh, great, whatever. But the point being here, that you cannot basically walk into a craftsmanship area and assume that they are interchangeable. They are not. And that's the nice thing. The interchangeability does not work because you have 4 weeks of something and then you get 2 glasses. They work though differently. So this is making glass by blowing glass. It's hot. It takes it's a very time sensitive project. It's like you blow, you rotate, you twinge and tweak, boom, done. You have to be very focused. It's ultra hot. You touch it, you come too close to it, you burn your fingers, hands, everything. It's very fun, but very intensive. Sweat like a pig. And then it goes, so you heat it up, you inflate it, you make a shape, then it goes into a heating cabinet. You cool down the temperature very slow, similar to the crystal, to not have tension in the glass material. Because if you cool it down too fast, like you can try that at home, take a glass, put it in the oven, and then put cold water to it. Because the material has too much tension, and that would happen with glass as well. But then this glass, and any glass you see, glass of my watch, yeah? Does anybody of you know what's the half-life of glasses? You know what a half-life is? It's basically, everything deteriorates in this world. Like, some stuff 30 years later, only half of it is left. That's a half-life of something.
Sand.
Huh?
Is it sand? Sand.
Sand? What is sand? No. Sand, yeah, glass is sand. Glass is silicon, that's true. The interesting bit is that glass is so hard that the half-life, so you take a little block of glass and you would put it on this table. Well, let's put it somewhere outside, okay? and you would wait till it is weathered away, yeah, it would take 1 million years. You have to get this in your head. That's really fun. Every single glass that you have around you is so strong that it would take 1 million years for it to wither away. That's crazy when you think about that. I mean, a plastic bag takes 2,000 years and it's gone. A glass thing takes 1 million years. So it's very funny when you make glass, you make something that unless you smash it on the floor and stamp on it, it will literally be there for a million years. And everything is time-based. So what I did was that I scanned these and then I cut them. You see that? I cut them into halves here. Cut half of them. And scanned them as a full one and cut. So then they existed, and that's a funny thing. Think about this for a moment. If I take two objects and I hold them apart from each other with a jig in a 3D scan, then the object, what is resulting from that in the 3D, is as if the two halves would be flying, right? So if I would 3D print something that works around them, I'll basically freeze the glass in a state of suspension. So here's a scan of it. And then in the end, I combine the 3D printed element onto the glass because they were fitted. And here you see some of the final results of that. The last bit of that is what I'll show you next time, is when you keep them apart, when you push the material of the 3D printing, but that we're talking with the 3D printing. Now this is our break time. I'm already 5 minutes over. So do you want to have the second part of the material lecture, or do you want to do the demonstration next after the break? Who wants demonstration and hands-on? Who wants second part and then demonstration? Oh, come on, this is so hard. No reaction. Okay, demonstration and then hands-on making a ring. Who wants to make the ring? 1, 2, done. Okay, fine. Now last chart. Who wants to have the second part of the material how to CNC mill stone lecture? Okay, no stone milling, done. We do ring next. So take 10 minutes break, come back, and we start with Rhino and 3D Max and more measuring. So I'll see you back here at 10:15. Not 10:15, I mean at 4:15. Ah, skunkworks. Yeah, that was fun. Good instrument. Ferromagnetic instrument. Fun. You guys want me to start the Zoom recordings for when I do some Rhino in case you... Yeah, oh, she's like... Okay. I've suddenly seen somebody so happy. So, yeah. All right. Fair enough. This is your friendly Zoom recording of the Rhino session. All right. All right. So, what we want to do today in our cool Rhino session is to make a ring, and one ring I did last week, just to check out stuff for you guys already, is I made this ring here. So this is, you can see the details are quite nice. It's a ring that I tested making and 3D printing. It has very fine details. It's made in black nylon, very durable material, very strong material. And yeah. So let's make a ring and let's see how far we get and see what you want to do with it. Okay. So here I downloaded a ring from the internet. It's a blank. And many things are very difficult with this, so I'm going to discuss why we are not using a blank. So this ring has been made for metal casting. which means it's very hollow. That's good. Great for metal casting. You save money, sure. Why are we not using it to make in our design? Well, we could use this, but it would limit our way of designing with meshes very much. Because it has very many fine meshes here already, because it is already cut, it's not a continuous surface anymore, it has a lot of things that are very difficult for us to adjust in terms of do something with it. Sure, you could take this ring and fluff a little bit around in Mesh Mixer with it or so, but we would not create a continuity in the ring. And one way I want to discuss today things is how do you work between Rhino and mesh modeling softwares? And we're doing this with the example of a ring, okay? Because it's a small little design object, and yeah, you can make one and we 3D print it, and you can be happy, because why not get a present from your favorite tutor, lecturer, professor of all time, Dr. Klein? Huh? There you go. What is the most important part of a 3D of a ring? It is the size of the finger. People who have a ring like myself, I'm married, I have a wedding ring, know that, yeah, you do need to know the size of the finger, otherwise you have a problem. And they get measured in diameters. So this is a 19 millimeter diameter. That would be maybe correct for you, maybe-ish. But for small hands, you go down to 17 millimeters. So by now being an expert in hands, I can guarantee you 18 to 19. If you make yourself a ring, then you definitely are 20. 17 to 18. That's definitely 16. That's 17. 17. So you get the drift. Most of you actually know your ring size anyway, in case you've ever bought a ring. Or bought a ring for your girlfriend, or for your mom, or for your sister, or for yourself, or God knows what. So we start with the ring size, which basically is a simple circle. Now, you can decide to make that circle in front, left, right, center, however, but I would prefer, out of somehow strangely understanding how a ring is, I always do that from the front view. So I start with a circle, and that circle I make in the diameter. Diameter it says up here, and obviously, please remember the basics. I'm going to say it only once today. Snapping to end point, near points, middle points. This time maybe center points. Make sure that you're working in the dimension that you're aware of. So go quickly to your setting. Check what the units are. It's millimeter. I think it's precise this time, so we should keep it in millimeters. All right. So little ring here. Diameter is switched on. Radius for diameter. So this diameter, then let's make a ring that is 18, say 18. Well, that seems to be wrong, right? Because clearly if that is 18 and that is 19, well said, and this is not the radius but the diameter. So click here, make sure we cut 18. Yep, that seems to be correct. I mean, 18 is my size as well. It's not my size, but it's a ring that I'm just making. If you make 20, you get it bigger, and so on and so forth. Alright? But you do have to decide on the size of it. Now, one of the things that we want to have as well, of course, so now you see I rotate it from the front view to the side view. If you are working in one view, if you prefer to now work on top view, that's fine as well. If that's what drives your boat. But remember, when we are extruding things or copying things, we are on this construction plane, so vertical means upwards, while the green axis and the red axis indicates that there will be no movement vertically. So well, the next size is obviously to make sure how thick your ring is, and within the 3D printing elements of SLS and SLA, we can clearly say to copy this ring by about 3 millimeter should do the trick. So if we hold the shift bar, type 3, and then we hold the shift button to make it orthogonal. Then we have the main constraints of our ring, which is that the size that it fits in, as well as the thickness of the band. That's a bit like my wedding ring here. It's around 3 millimeters in thickness. You can obviously make it thicker if you want to, but that's making more material. And it makes it well uncomfortable. Because remember that your joint of your finger, if you have a band here that is very thick, it will start to actually be a problem for your hand. Yeah? So making a ring that's like basically that thick all around makes very little sense. So let's start easy. Okay. Now what I did here now when we look at this ring is I layered 1, 2, 3, 4 different kind of folds into the ring itself. And how did I do this? Well, it's actually quite simple. First of all, I offset this ring, or I can make a second ring, second circle. I'll go back to the front view here. And here I can make a ring, a circle, where I snap to the center. See, you have to snap to the center. So when you go close to the line, it snaps to the center, see the end. And I know that was 18. So now I can do this by eye, just to give me a thickness. So here we go. Let's start with this. Okay? Be reasonable. So, and then I can take this line here now, which is the top surface of my ring, and I can copy it. And in this case, because I'm on front, vertical, from the center here to the center or near here. Now, if I were to loft this LOFT, I would need to get the right sequence. 1, 2, 3, 4. And you see here, this is the seam, so 1, 2, 3, 4, yeah, that makes sense. And if I put this to shade it, then you see if I make a loft from this ring, in normal style I get this, in loose I get this, in tight I get this, and in straight sections I would get the straight section of it. And if I press the close loft button, then I would actually get the whole ring even. So, and if I would go uniform, I get this. Okay? So, with this one, I would obviously make the ring smaller. So if I go to front view here, you see that this is my line of the 18 millimeters. So doing this command would cut my ring here a bit. So that's maybe wanted or not wanted. So now I say cancel. Okay. Now what could I do with this further? Now if I copy this, for instance, vertical, to let's say here, and I could take my second part here. And now I want to rebuild this because this was done as a circle. So circles are notoriously problematic, and I'll show you why. Because see, when I move this control point to the back, there's a kink here, because that is where the circle closed itself, because it's still in Rhino seen as a circle. And unless you like to have this kink and not a continuity, I would not recommend that. So what we do is we rebuild, like REB, rebuild. And you see that the point count of this ring, this is quite interesting, was 8 and 2. So let's stick to 8 and 2. And you see the maximum deviation of the newly created curve towards the old is 0.03. So we didn't change actually much. But what we did change is that instead of having this boundary box where you see we have like 1 point, 2 point, 3 point, 4.5 point, 6 point, where it is in this describing square, we now have a describing square that is by tangential lines to it. Okay? And that makes a huge difference. Because if I take, for instance, now, say this control point, this, and this control point, and I move it vertically, then as you can see, I create a very different line. If I go now to the left of this view, and maybe hide my little mesh in here, it gets actually even more interesting when I could draw these lines or move these points so that they line up. Okay? If you want to be even, so now it gets already more interesting because let's do our loft experiment again. So this guy to this guy to this guy to this guy to this guy. The lining up seems to be more of a problem now, so we could move this guy. Take the center away. Okay, so for the moment. So this is the open, and if I do the close, you see we get a self-intersecting surface here. That's a big problem. So we're not finished with that, but we basically get already a pretty neat element here, and obviously something completely crazy self-intersecting here. So this is not where we want to stop our investigation. So what happens now? What happens now if I take a middle part away, for instance? I just remember loft. Inner, outer, outer, inner. Maybe close this. All of a sudden this starts to become actually quite interesting. Of course it's not yet perfect because look, it makes a weird little double here and all kind of things, and if you go, oh, that's not what I want because it's very big. But you know, we're starting here. You can do it as well uniform, and all of a sudden you go like, hang on a second, this starts to look not too bad as a ring. As a blank, because we still have to do spikes and other things, but we are at the moment only working on the blank basically that we can then develop further. Okay, one of the things that I looked at it though is that this element here is not symmetrical. You see that? When we go to front view, this one is not in the middle. And that annoys me because it means that the whole ring here, if I would make a line from the control points, from point to point, this point here, it's actually not horizontal. So that really pisses me off. Because that means all my commands when I switch from left to front view or so are slightly wobbly. Unless you like asymmetry when you're building it, I would recommend not working with this. So what happened here is when you look at the outside, so let's go to the front view. If you look from here, we made a circle. When I spanned the circle, I basically went, see when I put the circle command, I went to the center of this. And then instead of doing it vertically, I did it just somewhere. And that basically sealed that point. So what you should try to do is to do this always in the right way, like to hold the shift bar. Okay. Right? That would make a huge difference. So now we delete this guy here. And then if I select this guy, you see that actually now the control points are completely symmetrical. And that will stay even if we copy this, even if we rebuild it, as discussed, with 8 and 2, the same count as it is. You see, tada, it stays symmetrical. So keep doing things symmetrical, so it will make it, I mean, not symmetrical for design purpose, but if you are having your control point symmetrical, everything will be easier. Look, I show you why, for instance. If I take this ring here now, this circle, and I copy it vertical, let's say to where we had it, And I now from the side I look at left. So now I decide to take this and move it. And to take this one and move it. So you see, because they are symmetrical, I basically create one line in profile. And that makes everything already a tiny bit easier. So again, I try my loft now. And these things matter in the end, I show you that. Oh, I lofted it correctly. See, I now very carefully made sure that the seam curves are where the knots are. One curve, there's a knot. So you have to use the quads of the knots. And then close the loft. And you see, if we then go to uniform, we get actually a very tight fit ring now already. Very clean design. No kind of wobbles anymore. None of that, asymmetry, everything happier days. So let's say okay to this and take this ring and move it out of the way. So we got already one blank that is quite unique for Rhino. Let's go further. So if we do what we did here, yeah. So we got our little symmetrical guy, and we copy it. And so if we now go, remember that thing with the valley and all that, what we once did? Valley and not valley. So let's apply this idea about valley and ridge in here. Right, let's go left. And we hide our ring for the moment, it's easier for us to manipulate. So move this to here. And then move it actually upwards. Okay. Now we can bring that guy, copy it again. Take this guy again from the left view. Maybe we take our final one here. So now this is getting quite interesting. So the curve of this loft will now have to go from the inner to the outer, to the outer 1, outer 2, outer 3, outer 4, inner 2. The seam curve is correct. Uniform, close. Interesting, huh? Now we're getting actually a really interesting profile ring already. So we can have continuity with at the same time, so we keep it very tight on the back. And it can be expressive at the front of the ring, which is obviously functionally clear because, as you know, you need to grab with the ring, and it doesn't matter how big your ring is here. If you have like a giant 10-carat stone here, you still can use your hand, but if you start to do things here, then you will hurt yourself, right? I mean, you can obviously design what you want, but end of days, you can do as expressive as you want on the front side, but you can't do much on the back side. I mean, unless you want to make it unfunctional, non-variable. Okay, so let's for a moment stop here for Rhino and look at this. So one of the things that Rhino is really bad in is to actually manipulate these faces. That's really hardcore difficult. I mean, there are some sub-D tools now in Rhino 7, so we could do something with subdivision modeling, but it is very painful. So I would not recommend you to do this. Never ever want to recommend to do that. So hence, if we're going from this and we use now the full power of our Maya, Blender, etc., as you can see, in Rhino, even if we take this wing, this is just the surface, so we could literally actually start manipulating the polygon surface. We would still only be able to do that surface. This is one type of modeling. The other type of modeling, where we go and we use the kind of gradient curvature between here, is called topological modeling or mesh modeling. But for that, and this is a really, 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 really crucial part, for that to happen, we need to make a mesh from this NURB surface. Okay? That's really, really important. I mean, you can play a bit more around with it, but I wanted to start showing this now. So why we use the uniform is if we now talk a mesh command, we will get this very simple option where we can preview how it's meshed. And you would say, oh, look at that, that's really good, it's very fine. So let's say okay for the moment. So what we get here is what I call a complete dead mesh. Now why is it dead? It's dead because it's refined, it's perfect, it's nice, it has some problem here. There's a weird edge line, which I don't know why they're triangles. I don't know why these squats are bigger than these squats. I see many of these triangles. You want to avoid, if you are wanting to work in a 3D mesh modeling software after Rhino, you need to avoid any form of of triangles. Triangles equal bad. We do have as well a bit of strange things here, but that's okay. Look at this, all of this stuff, crazy, crazy stuff, really difficult. This, if you just want to 3D print this, you're done. Make a mesh, because we can only 3D print meshes, save it as an STL file, and that's it. But if you want to manipulate this in 3D Max, Modo, Maya, Blender, any of these things, this is a dead mesh, you can throw this away. This is not usable. Or if you use it, it's painful, really painful to use. So what we need to try to get here, and let's type the mesh command again, is to go to the detailed controls of this, okay? And here we have a lot of interesting things happening. We got density. So we can preview that, and we get the same what we had. So if we reduce the density, let's say, or let's put it further. Let's go to the max. One is then the highest density. Then boom, we get like a crazy dense mesh, even better than this one. So this one is even better for 3D printing. You just go down, click, 3D printer, sorted. But if you don't want that, it gets more interesting. So if you go to, let's say, 0.2, then you get a much coarser mesh. A mesh that if you are doing this in 3D Max or Mojo or Mesh Mixer, you can manipulate a lot more. So let's keep that for a moment here, just so that we keep track of the process of what we're doing. So this is a medium dense mesh, this is a low density mesh. But of course you see as well, like everything gets very jaggedy and all that. The other problem that we have with this jaggedy mesh is that we still have a lot of triangles, and these triangles are very annoying. Again, we don't want, in the end, ideally, our ideal goal is to have a mesh without a single triangle. So we have to go back to the mesh. This is really an art form where you will see, if you make the right decisions here, they will carry on all the way in your design, all the way. And you can never go back to it. So you have to spend some time on it. So what happens, for instance, if I preview that? Okay, let's see, what is refining mesh doing? Nothing. Jagged seams. Oh, what happened here? Jagged seams gives me only quads. Now hello, that is interesting, right? So if we go a little bit higher, 0.5, by the way, you have as well the help on the side here that automatically tells you what you're doing, just so that you know. So here you have always a little help, which is on automatically. So that can give you a little bit, to mesh. Here you basically see as well as animations. And here you see the trim, blah, blah, blah. And then here you see basically these things that I just talked about. So one of the things that I just did, minimum edge length, maximum edge length, maximum axis difference. Where's the little ones? simple play right here. So here we got jagged seams. Because if this option is true, all surfaces are meshed independently and Rhino does not stitch the edges between joint surfaces. So you see that, no stitching. Instead, we've got a mesh created with jagged seam on the left and disabled on the right. Magenta edges left are naked edges, and that's obviously a big problem. So we are forcing it here to abandon the kind of stitching between it. So let's say okay to that and look at this mesh for a moment. So what do we get here? We get a very, very clean mesh that only has, see here. Now here gets the interesting bit. Here we basically, that happens with the jagged seams, we basically get two meshes that don't match each other. And if we get that, we can't really print it or can't work with it. So now we basically have, most likely if I ungroup this, four meshes. 1, 2, 3, 4. So that's really bad. We don't like that. 1, 2, 3, 4. Don't like this at all. Not good. Which most likely has to do with that we have 4 surfaces here. So if we explode this, we most likely get 1, 2, 3, 4. So we don't like that either. So let's go back to our lines. This is really important that you understand there's very, very important differences between continuated surfaces and not. So what did we do wrong here? We tried to loft. And we lofted again. Yes, I know you're getting bored of that, but I want you to make mistakes. Because only that way you can see the difference between all these lofts. So here we got our thing. That is good. Okay, we got it uniform, we got it closed. And you see in the visualization that we get these big seam lines happening. And that is where now comes the magic, okay, ladies and gentlemen. And that is really, really crucial because many 3D models will never get to that state of knowledge that you already possess now. Because this has all to do with either precision or the purpose of what you're using it for. And our purpose is to make something in Rhino that is really specific to Rhino and then push it into another software to do something with it that's really specific to another software. Yeah? So we want a perfect one surface, not 4 surfaces, that is very elegantly symmetrical and that we can very elegantly mesh into something where we get only quads out. So what we need to do is we need to rebuild this here. Rebuild it with our control points. And if we rebuild this, let's say with 30 control points, then it looks like this. And what you see is we don't have any seams anymore here. Okay? And it's about 20 or whatever you want. So if we are looking at this guy now and we're moving this out, and I'm sorry that I'm making you to sweat so much with this project, but it's very important. So if we mesh this guy now, and we work with jagged seams, and we do a preview, we say okay to that, and we move this away, and we look at the outcome of this, then we have, ladies and gentlemen, a perfect line of quads, where all the quads meet at exactly the points, which means it's continuous and not what we had here. Remember, what we had here is, these are the worst type of mistakes. You cannot fix them, ever. Like, you would have to manually shove all these points, and it's a fucking nightmare, freaking insane. So where we need to go is like, we need to make these models that are perfect quads and continuous surfaces, which means this ring that we just created is the perfect game asset. This shit, you could sell this on really high money in the internet. Because what people are looking for are not triangulated shitty models, because those you can use for nothing. They have too high polygon count. They are not worth you cannot manipulate them. But when you are getting a blank like what we just created with like perfect quads, perfect seams, that stuff is, you can put this into any mesh modeling software and go happy days. And I'll show you how. Don't worry. So this is the epicenter of happiness for any 3D modeler. And those of you who know 3D modeling in Blender, Maya, etc., they know they love this, because this body here, that's where it's gold. So this is what we export. This is the state you need to get in Rhino 2 to understand meshing, lofting, curving, and continuity of surfaces. Very important. The next step is to export this. So all we have to do is file, export the selected, put it on a desktop, call it maybe a OBJ. OBJ is the most versatile export and import software that you can get. Like, it's better than 3ds or so, or FBX, because it has unlimited face counts. It just never makes problems. So use this. Give it a good name. There we are. Now you get up some weird object things here. Formatting Windows, unless you work on Mac, of course, that you need to do Mac. Map Z to OBJY, don't do that, because unless you work with the software where X and Y and Z are changed, you don't need that. Mesh unmodified, very important. So okay, basically. Let's look at this ring now, for instance, in Mesh Mixer first. So just to check it out. So we import now our ring. Here it is. We click on the shader and we push a shading material onto it. And you see this blue thing means it's open. So that's bad, really bad. But then we remember these are just seams. And there is a command for that under edit that says close cracks. And with one click, we make that thing into the perfect 3D model. One click, close cracks. All right, done. Happy days. Woo! So cool, huh? Okay. So we've done that. We have our inspector. We can run that over, check if everything is fine. Yep, no mistakes, nothing. Great, fantastic. I repeat that for people who were still busy. So I'll go back. You import it, and you see that because Rhino still makes these seam lines here, that's because it is still, this guy is made explode from one surface. It's made from one surface, but that one surface needed to be generated in some form. So you see it creates these slightly darker lines. And that means that in this software it's indicated that it's made from 4 pieces. 1, 2, 3, 4. But as these lines lie entirely on top of each other, we can go to the edit command, and in there we have this close crack. You can only do that when these edges lie exactly on top of each other. And then within one click, ta-da, done. Now, of course, from here you could do something as so I will save this now, file, export, put it on my 18mm fixed. And of course you can go now with your brushes and do crazy things here, I don't know what. I mean, I wouldn't do this now, but you could do whatever you want onto your blank, and I don't know what. Call that a ring. I call that a disaster. It's like, who wants to have that? Nobody wants to have that. Exactly. That's your eyes are the perfect things. Like, I don't want that. I mean, if my boyfriend gives me that, it's like, no. But what do we have here now? Look at the wireframes. We still have the perfect little ring here. Really neat and nice, all happy. Although we have triangles. You gotta be careful with Mesh Mixer. Always be careful. Now let's look at 3ds Max, or Blender, or your favorite other mesh modeling software. If we're going to 3D Studio Max, I'm just going to import this here. File, import, go to desktop, get my 18mm OBJ ring. Done. I'm going to not retriangulate it. Import as a digital very important, do not re-triangulate the polygon. Very, very important. Do not flip the XY axis. And that's all cool. Record it. Here it is. Boom, my ring. All good. Happy days. A bit black, but that doesn't matter. Okay. If I go to now under fold shading, you're clicking on clay. And here's the ring. All nice. And you can click on that again. Etched faces, and now you see the faces. Oh my God, so beautiful for 3D modeling. So good. And as you know from like other softwares, Modo or Blender or so, you can now interact with these faces quite neatly. So right? I mean, these things you know, I guess. But if you don't know, let me show you some nice things with this. So these are called faces. And they are quite useful. I mean, I must admit, I haven't used Max in a long time. Let's say, for instance, we want to use a little bit fun with these guys. So edit polygons. In polygon editing, we have basically 3 ways to interact. One is to push out, one is to pull in, and one is to connect. That's it. So I'm going to demonstrate. If I'm pushing out, I can use an extrude command and use that one either as a group or by polygons. Extrude commands are smarter because if you use bevel commands and you use percentage, while in extrude you use numerical values. So that's quite useful. So if you wanted to do this, for instance, you push it out. Okay, yeah. And you can at the same time scale all of them. So you go to your regular menu. You have a scale button up here. So we got already nice spikies coming up. Well done. Okay. I can go back to your regular selection. And one of the things that you might want to check out is you can put a smoothing command on top of this. So that's in 3D Max, it's called a turbo smooth on the side here. Turbo smooth. And that basically shows you how this would look if you smooth it twice. So that's subdivision modeling. So now you're getting into this organic shape already. And you can switch this on or off just with making the eye on or off. Okay? That means, for instance, if I take another stance here on these guys, on my polygons, open here, polygon, and select some more. Now let's do a second row, but in this case, let's use, for instance, an inset first. Here that is by group, let's do this by polygon, and then a small inset. Okay, and then an extrude. And we can make this as well a bit smaller. And then add the scale on top of that. Okay, good, good, good. Now let's look at how this would look if we switch on the turbo smooth. Now you see having added that inset basically means that you have a clearer definition on the bottom. Here, because the subdivision of the polygons means each polygon gets negotiated into 4 and then into 8. But so if you have a small polygon as an inset here, see, there's a small polygon, then smoothing that would just make this stronger as an articulation. Okay? So these are quite big differences between between insets or not. These are still spikes. Now what we can do as well is, of course, we can work with the polygons. That's what I just demonstrated. But remember, I said something about that we connect or we extrude or we set inwards. So one of the things that we haven't shown here is let's connect. So if we do another inset here like we did before, okay, and we flip this thing around here. So I guess it would be here. This is maybe where you could work more with a, I don't know, you could go wireframe even. So that does require a little bit more imagination, but not too much. You see, because we work basically in such a stringent, strong manner that our faces are so well aligned that it's very easy. So now I can do the inside here and the inside. Okay. Now if I connect, if I take for instance this guy, and I connect it to this guy, I can do this via a bridge. That's the next one. Bridge is here. So you see, it basically pushes a hole through the whole thing. Here we can say how many segments. I would always say for this like 2 segments. You can decide if you want to squeeze it or not, which is here. But again, please don't intersect it. Okay. Say yes. Okay. Now if we go back to our shaded, our clay modeling, and we switch the polygon off, go back to the turbo smooth, switch it on. Okay, now we basically get a ring. So we have spikes as expression outwards, and we got holes already going inwards. So that's pretty neat. We can obviously combine them. We could basically make a combination between the two, for instance, go to the polygons. Take for instance your spike and your polygon here. You can do then again an inset, but now as a group and not as individually, which means it combines the two. A nice little combo move we could call it. And then take for instance these two as well. So now they are selected, bring in your bridge. And there you see that it twists, so we gotta be careful that we have the right ones. And gotta make sure bridge. Then sometimes it twists itself, as you can see. So then we use this twister to untwist it. Oops. But it might be because that guy's too far that we can't do that. You see, it's basically not working, so don't do that then. Or bring it down to 1. So you see that I still interact with this command. So I can still basically play with it, add more to it if I want to, for instance, on both sides as well. So this is a very interactive command. And do this till I'm happy with it. You could even switch the turbo smooth on. Oh no, you can't do that during the command. And using the Alt button, you can deselect. Alt or Control. Alt, Control. Okay? Till you're happy. Or Control Z if you're unhappy and okay, I don't want to do it, please go back, go back, go back. There you go. Okay, these are faces. You can do the same operations with edges, which are these lines here. So you can, of course, and that's quite fun, make a ring. So this is a very interesting way of selecting things. So if I want to do this globally to the whole ring, I could, for instance, go to the edge, as you can see here. I selected one edge, yeah, and then I click on ring, and that selects each in one direction. If I select loop, it selects all of them in the other. And this you can, gentlemen and ladies, you can only do that because we model so clean. If we would have triangles or so, you can't do these selections. So now we have, for instance, this guy, and we could do a global thing through this ring. For instance, let's, for instance, extrude this line here now. So you see, we are extruding it outwards and sideways. So we could do, for instance, this. Might not be a smart thing, of course, but that's something else. One thing that you see though is that we created a little gap here, and that is because our seams were not closed, but we can fix these later, that's okay. The same counts then for our points. You can work with the vertices here. You don't have a ring, of course, because they don't know how to do that, but they're not like ring connected, they are individual points. But yes, you could use the points, for instance, to make a different type of spikiness, because if you extrude these guys, or chamfer them, actually let's do extrusion. It's very nice. You can actually quite, so this is called topological modeling. And yeah, and when you're done, you say yep, and you can look at this troubleshoot. And obviously get rid of the edge faces, and you can see it even better. Oh, it's getting quite something. And it's interesting because this is maybe a moment when you should hold in and look at it. So we use the curvature in Rhino, right, to basically create the faces. And all the options that you do in topological modeling are perpendicular away to the curvature of the ring. So you see then these global shapes here, they're basically following the curvature. And so when you set your curve smart, the topological modeling afterwards, whether it's spikes or bridges or other things, they always will follow. And that's kind of making this really smart. And remember, you can combine these elements. I only showed you very simple things here. Look, if you go further than that, let's go, for instance, to this guy, bring in the edges. You can do this for days. It's really fun. I mean, I can do this for days. So if we do again an inset, for instance, let's go for this guy, this guy, this guy, this guy, this guy, this guy. Inset. Not too hard. It needs to be still remaining. So you have to see that these are not self-intersecting. Okay. Then I could take this guy and this guy, or this. So there's the bevel function. Bevel by polygon. This is not that much. I don't know why it's always 7 to 10. Now I could create this as a bridge. And if I switch off on the turbo smooth, ta-da. So again, even if you are building secondary and tertiary layers by topological modeling on top of it, you still basically, you're still following the logic of the primary surface that you set up. I mean, now we're getting quite complex here. This stuff is looking like already pretty neat. Just imagine if I follow the ring, and then I could even build in a gradient, make it smaller, so high, to small. But see, this is maybe the most crucial 3D modeling lecture you're getting, is you set up the logic of the model right at the start. And then from there onwards, it's just following it through. It's not really much doing more. All right, so it's 5 o'clock. I think it's time for you to start with your rings if you want to, and I will help you if you want to, and then we can go for 3D printing if you have something in the end, or if not, then you just have fun learning about how from NURBS modeling surfaces to meshing to topological mesh modeling, you can use these tools. Let me check it. Does anybody have 3D Max open? Because there's one for two. Blender. Somebody's working with Blender. But you went for these triangles, so you have a big problem. Triangle for the lady. If you have 3D Max problems and you want to at least do a ring, don't do it. If you hit this ring, people will think you have problems. There is symmetry commands, so you can go to things like that. These are here. A little bit, but I would really expect Ooh, nice! Up there. Wow. Beautiful. Wow, yeah, that's a good idea. Yeah, totally. But nice design. Ooh, asymmetric.
點解佢有個選擇框出嚟？啊係啊，review 咯，中間 review，唔係後面仲要係20%，係咁樣，跟住再。
Yes.
close 咗佢，你閂埋佢，係 OK，跟住出嚟嚇，唔知啊，我唔知佢點，佢係撳好似大圈細圈，跟住沿住佢，再去大圈細圈咁樣，細圈大圈，細圈大圈。唔緊要啦，打完佢。close 咗佢 ，close 咗。我唔知佢個 set 係點。就要俾呢個先咯。呢 OK，跟住再 match 咯。再 match 跟住打翻啲嘢。係0.2啊，跟住打0.2啊。條腰啊，你就同 OK， 應該就合埋一齊嘅。係合埋一齊。佢特登做出嚟嘅呢個，跟住合埋，係咯，係原來係一個好嘅 match。係啊，合埋。移出嚟先啦。呢個咪啱咯。呢個嗰個人應該死咯。ABJ 嘛，最 general。跟住係啊，第一個係係唔好Mac 嚟嘅，Mac 嚟嘅，呢個硬色嘅，啲 Mac 嚟嘅。Match 係呢個我唔係好記得啦，係啊，unmodify 啊，係咁咯。OK 啊，跟住佢話好似 match 就唔係咁好喎，因為可能你試下撳，唔知邊度撳咩 close 咗。或者你用
Then look once, okay? So working match. So this is really important that you get it right here before you bring it somewhere else. You bring it somewhere else before you fuck
係你
it.
識用嘅，So
you have controls. Preview. You got
唔使啊 ，match
the match
話唔使用 X 嗰啲喎，用電腦嗰個啫，係咁就係咁。
Oh,
佢係 match 嗰隻，唔使啊，唔使啊，佢用乜元素？佢用乜元素？
The most crucial part, really, is super important. You bring over a low polygon mesh because the subdivision modeling, you can always make that as smooth as a baby's bubble. Like, it's easy peasy to increase the faces, it's super hard to decrease it. Okay. Blender or Maya or low polygon, nice square evidence. That ring is also ring. That's nice, I like this. Das war jetzt nicht die Omidismus. Oh, you want to do a sharp edge? Well, that's what you cannot do. Jesus Christ.